Welcome, everyone. Thank you for coming. My name is David Yiptong. I'm the Manager of Acceleration for QAI Ventures, specifically the QAI Ventures Canada iteration. For those of you who don't know, QAI Ventures is an early-stage quantum investor. They're based out of Basel. They actually came out of a family office. Thomas Sorinn is actually part of the Schindler Elevator Company, and the family decided they wanted to invest in technology and in something that would really have a positive impact on society. So QAI Ventures is based in, as I said, in Basel. We do a lot of community building and ecosystem building in addition to investment. This is the logo soup that you see here is part of the ecosystem that's being built out in Basel and part of the partnerships with QAI Ventures. And my role, I mentioned QAI Ventures Canada, is part of the international expansion that has gone on. QAI Ventures has partnered with Quantum City, which is based out of the University of Calgary. And we are actually running the accelerator program in Calgary in March. So this will be the first iteration of the accelerator outside of Switzerland. We do a variety of programming. We all know that quantum startups are very, very early stage. So we do want to provide them sort of a long range patient capital to help support them through their journey. So we do have a variety of programs and funding. This is our current portfolio. You can actually go to our website and see an updated version as well. So we do invest in all areas of quantum, not just quantum hardware. And with that, I'd like to thank the organizers of Q2B for inviting us to actually work together and actually put together this pitch competition for you. So what you're going to see today are 6 quantum startup companies, and like all things quantum, they exist in all phases. So you'll see a wide range of companies. Each presenter will get 5 minutes. So for the presenters that are here, I will be strict on the 5 minutes. You'll see me raise a sheet of paper saying that you've got only 1 minute remaining. And then we have a panel of judges here who will ask questions, and they have up to 2 minutes for Q&A. So with that, I'd like to introduce to you the judges. We have Chloe Archambault, who's a partner with Quantiset. We have Celia Mixbacher. You know what? You just told me, and I messed it up. The executive director of QEDC. We have Adam Benet-Watts, a scientist in residence at Quantum City. And we have Gregory Peters, a board member with Qubits Ventures. So I'd like to thank all the 4 judges for taking their time out, because I know they're all busy. They all ran from meetings to come and do this. And we are going to get started. So I'd like to call the first presenter, Sophie. Is she in the room? The stairs are here.
Thank you so much, everyone. I'm just so excited meeting quantum superstars in person. I'm having a great time. Quantum AI is a quantum Gen AI company. So we do quantum machine learning as well as Gen AI. So Gen AI models have, they revolutionized AI, but we have too many parameters to train, resulting in high computational cost and high energy consumption. And we bring quantum to the rescue. With quantum Gen AI, using photonic, continuous variable photonic quantum computing, we can have lower parameters to train, and we can have faster convergence. So an example of a model in classical would require 33,000 parameters, and in quantum, we would need 228. That's going to lead to lower computational cost and lower energy consumption. So quantum AI has 3 distinctive product lines. Quantum neural networks, that was developed by Xanadu up in Canada based on their chip X8. We have a faithful implementation of classical neural networks with weight matrix, bias addition, and non-linear activation function That is not possible in the qubit-based model. With that idea, we come to transformer architecture, and then we replace feed-forward network, because it's a neural network, with quantum neural networks, and that was the reduction of the number of parameters you saw from 33,000 to 228. And with that idea, now we can build quantum large language models, because large language models are composed of blocks of transformers, and then supervised learning layer, which is neural networks, and then reinforcement learning that are implemented using neural networks. So they all can be quantum neural networks with huge computational savings. Yeah, I have way more number of slides than the actual time that's allotted to me. Why quantum now? We are here with KGAR running at 48%, 31.5%. It's some, it can be some thin number plugged out of thin air, but we all know that we are at the beginning of some kind of revolution in Gen AI and quantum computing, and we are here to take advantage of that. In terms of market, we are not going to go to anybody on the street just because they have a lot of money and they have enterprise solutions. We are going to the people who've been working in the quantum space, exploring AI, such as JP Morgan Chase, pharmaceutical, energy, automotive, manufacturing, government and defense. We have very, very specific industry verticals, and we are to hire AI engineers with those specific domain knowledge. The competitors, a lot of them are hardware companies or full stack, hardware, software, full stack solutions, or some kind of platform or software. But I haven't really seen anybody with very, very specific quantum AI solutions. Projected revenue, a lot of it is going to be subscription based and consulting based. Projected revenue based on the market, but of course it's going to depend on the pace at which we can achieve our milestones. We are looking for 1 million ask. That's going to hire maybe 2 or 3 engineers to actually build use cases in drug discovery and battery material discovery. Like we have AI engineers standing in line. I spoke with a lot of people today who are very interested in partnering to build use cases. So yes. So this is our team. Some of them are kind of loosely affiliated, waiting in line to be hired. But that's kind of where we're at. Thank you so much for listening. Do you have any questions?
Sure, I'll start with a technical one.
Yes.
So your quantum large language models, or your quantum neural nets, I should say. Can you tell me a little more about the hardware, sort of qubit counts? Like, what's the quantum piece?
Yes, the quantum piece of that is, this is based on the continuous variable quantum neural networks written by Nathan Killeran at Xanadu in 2019. So it's based on continuous variable model, which is not qubit-based model. And then they actually have their chip called X8, which operates at room temperature with 8 Q modes. They're not using elementary particles to actualize qubits, but they're using waveguides, which they call Q modes. So you have classical light from laser source. They're squeezed and turned into quantum light. You operate and you measure at the end of each waveguide the number of photons observed. And then Xanadu has strawberry fields for building quantum circuits, and then Penny Lane as a wrapper for quantum machine learning. So our code is in Python using penny lane for quantum circuit and a TensorFlow or PyTorch for actual training.
Cool. Thank you.
So we all know that today's quantum computers are not as powerful as we wish they were. Have you identified any use case, small scale use case or beachhead market to start working on projects with?
Yeah. So I spoke with you, and then ever since I didn't really have the time, but we were working with like a toy problem of iris data set. We actually achieve above 90%. So now we actually want to build use cases because the people in specific industries, they want to see how these models are being used for their specific problems. And I think I spoke with a gentleman for drug discovery, genome sequencing, that kind of thing. And I'm getting some other data sets, I think, from industry that we can start building together. So yeah, we are getting there.
Can I ask one question?
Yeah, oh yeah, quickly.
Do you have a sort of, you didn't show a roadmap, so do you have a date when you're going to be ready to start, delivering product?
Oh, the product we thought, now like, AWS Bracket wanted to feature us on their marketplace. And then for me, I thought, well, it's just a model, just algorithm. So I was kind of hiding away from them. And then now I'm encouraged to go back and they can put it together so it can be featured on Bracket. In terms of the algorithm to build actual models for Novo Nordisk or BMW for drug discovery or battery material discovery, novel battery material discovery, we can actually build it together. So yeah, for consulting, we are actually ready. So we are like right around the corner with some polishing.
Thank you.
Thanks. Next up, Brandon, are you here? There we go. Superconti Karma.
Hi, this is Brandon from SQK. SQK is working to solve one of the major problems, which is the adoption of the quantum computer is slowing down. So the problem is the complexity and the difficulty of the migration of the classical workload to the quantum computer. And today, I'm so excited to present QCOS, the solution to this problem. Okay, we're planning to launch the first QCOS service in next year, like the end of next year, probably. And we have based on the Quebec, Montreal, Quebec, and we also have the dev center in the Vietnam and Korea. Okay, the problem is, we see the problem is customer is hesitation to adapting the quantum computer because the researchers are strongly resistant to modifying source code that has been optimized for many years, which is the scientific workload is really hard to redevelopment. So the solution is the QCOS, the versatile HPC quantum migration framework. Okay, this is the how to solve the problem because the QCOS enables for the classical workload to the quantum computer as well as the classical accelerator too. And also, so QCOS is the base transpiler for the heterogeneous process unit, including the quantum as well as the other accelerators. Also, we adding the additional external workflow manager. So there's application to application in top. Yeah, we handle with those like the within the pipeline. So QCOS enables the quantum the computers for migration, and the how we do it is we share the execution space for the quantum computer processors and also classical unit. So the clients, they don't need to change much of their original source code, but it enables the quantum computers with very less hassles. So this is how our quick course to generating the QAIntum file for ready for the quantum computing. And this is our the demo system, and it's ready now. So if later this pitch competition or later, you can inquire us for showing the demo. And this is how it looks like for the UI. And this is the typical demo scenario. So we kind of actually running the MATLAB or OpenPOM the quantum espresso, and then it enables the quantum hardware in the backend without hassle. So that is about it today. Thank you. So questions?
Yeah, can you give me a little bit more color on how a user would go about using this, and then how do you deliver that to them? Are you delivering them a software toolkit that runs on their system, for example, that
Yes.
does this transpilation? Does it do it in real time, or does it do it prior to run? Or
It has to be prior run and also real time for the backend support, because the transpiler actually works for the transpiling for the later another compiled assembly. But within the just-in-time pipeline, yeah, we there's another workload trigger to the event, and then we're trying to trigger to the compilation, and then migrate to the assembly, and then ready for the embedding for the quantum workload and do it. Because we're adding the super quantum station, the workflow manager, which is, yeah, it's necessary for the multiple application running into a single pipeline. Yeah, and we accept those requirements and doing it our platform.
And a follow-up. So if I was a MathWorks or ANSYS user, then this is transparent to me at the high level.
Yes.
But at
And
a lower
then
level, it
the
works.
post-action, we have to wait for the data result from the quantum hardware, and then the measurement is done, and then we get it back, and then we are reprocessing for the post-process for the create the result.
Okay, and then last question is, how do you validate? Did you have some MathWorks design and you validated on different ones to make sure that your transpilation actually got the job done and didn't create
Yes,
errors?
our prototype, our POC project, we validation for the RMSE to how close to the actually classical processing result, and then we validate with this is the RMSE result, and it close to 0. So yeah, we're confident for the the small qubit environment. Our Q course works as the classical computing.
Yes, my question is, who are your main competitors and how do you compare?
Our main competitor. So the many kind of transition to the the HPC quantum hybrid environment. So, and with this kind of the client convenience service is for the strange works willing to do it, and they are kind of focusing on the front end automation, not just us for the back end automation. So, but the concept and then targeting audience is similar to us. Done? Thank you.
I'd like to invite Sorinn to the stage from Transilvania Quantum. No one runs to the stage when we call their name. It's not like...
Yeah, thank you. Hi, I'm Sorinn Bolos. I represent Transilvania Quantum, and we are a startup from Romania that does system software for quantum computers. So we developed a platform for quantum computing providers that allows them to offer easy access to their platforms. So this is built around the concept of workflows that makes it easy for newcomers and flexible for experts. So to understand how it works, imagine you are a chemist that works on exploring the properties of a molecule and use classical software on your day-to-day job. You've heard of VQE, but you have no idea how to run it on a quantum computer. So what you need to do is you need to find a vendor that has our product installed. The vendor has a predefined workflow and has made it available to all users and has also written a documentation for it. So what you need to do is read that documentation, map the parameters according to it, and then call the API to get your results. For the second use case, imagine a quantum expert which does complex experiments on quantum computers. So he reads about a new error mitigation technique that just came out this week, and he decides to use it. He needs to use it in his experiments. So because it's so new, he needs to code it up himself. He can log in the platform and upload that a code block with his implementation that can have both classical and quantum resources. Then he can publish the workflow, which will only be available to him, and use it as part of his experiments. So I hope that sums it up, why it's easy for newcomers and available and flexible for experts. So the team building this, I'm the CEO, I'm a software engineer with a lot of experience, most notably with systems software engineering for cloud. My co-founder, Radu Marginian, has a PhD in physics from Ohio State University. He also has a lot of experience in software and is an avid contributor to open source quantum SDKs. We also have an advisor, Adrian Colesha, who is a professor of cybersecurity in the Technical University in Cluj-Napoca. What have we done so far? We've built an MVP during the month of September, which included user management, job management, but did not include workflows. And we've talked about a number of about 10 vendors and university labs that that are building a quantum chip. During the middle of this period, it was clear to us that we needed to add workflows to our offering. So from the last persons we talked to, we got good feedback on the workflows. The market of system software is from $100 million to $200 million. We got that from multiple sources and also computed ourselves. And this solution with its flexibility is pretty unique, but IBM has something similar with Qiskit runtime and Qiskit functions that can be uploaded by third parties. We also partially overlap with integrators like Amazon Braket and Azure Quantum, and we also compete with in-house solutions. We asked for $200,000, which will last us for 1 year. In the first 3 months, we plan to complete our MVP. In the first 9 months, we plan to acquire 9 customers, which will give us enough traction to raise a seed round. And we also factored in an additional 3 months of runway. So if you want to know more, visit our website, contact us via email, or come talk to me afterwards. Thank you.
Questions?
Sure. So I guess what unique challenges do you see in building a quantum workflow as opposed to just a classical one?
There are no intractable challenges, so they are all solvable by software that we have today.
But
in terms of how to build the actual workflow itself.
What do you see as the biggest differences between a quantum workflow and a classical one? You know, what's different about it?
Well, I think the managing of classical resources and quantum resources, that will be so now if you want to use IBM, for example, you will wait a lot in the queue. If you want to build a VQE, you need a session or some kind of exclusive time frame that makes sure you don't overlap with other users. So managing this kind of having using in full the quantum resources and the classical resources without having gaps, that's an interesting problem. Thank you.
Thank you very much. I'd like to invite Nathan. It's this button here. Good luck.
Howdy, everyone. My name is Nathan Arnold. I'm co-founder and CEO of Photon Q, and we are a hardware company developing quantum memories, and we're also participating in the current cohort of a duality quantum accelerator based out of Chicago. Oh, there we go. So I probably all agree with me when I say that quantum is going to enable some of the most exciting technological advancements of this entire century, with applications such as novel drug discovery, development of new, stronger, lighter materials, as well as the ability to tackle some of the most complex optimization problems that plague every industry today. But unfortunately, as you're all probably aware, we're not quite there yet. And this is because quantum technologies are really hard to get right, and we need a lot of different quantum systems to work well together. And one of those quantum systems is a quantum memory. So just like your computers at home and the ones in your pockets have RAM in them to store information while it's going through a computation, quantum computers need a similar RAM-like memory to store quantum information. So I want you to imagine the RAM in your phone or in your computer, but it has to be cryogenically cooled down to a few Kelvin. It's also extremely high loss, so there's a high probability that it just loses the information it was storing. And it's also very error prone, so in the few times you do get the information back, it gives you the wrong value, say a 1 instead of a 0. And it's also very low versatility. So imagine if your computer could only store JPEGs as a file format. It's just not very useful, not very practical, and unfortunately this is the state of many quantum memories today. So the problem is that virtually every quantum memory operates in the exact same way. They all take quantum information in the form of a single photon, and they convert it into a state of matter for storage. So they convert the photon into a gas, into an atom, or into a molecule. And it's actually this conversion process that leads to all those issues I just mentioned and more. So our solution at Photon Q is to get rid of this conversion step, and we store the photon as a photon by storing it in free space. We utilize the fact that it takes about 1 nanosecond for light to go that far. So if you give it a long free space path in a controlled environment, then you can store it by a proportional amount. So by operating in free space, we have a bunch of benefits. One of them is we have extremely low operating costs because there's no cryogenics, there's no oven, there's no vacuum, it's just air, which is free until the government finds a way to tax it. We're also able to benefit from really high performance bulk optics. So these optics enable us to achieve really high end-to-end efficiencies that competing integrated matter-based systems just cannot benefit from. Our technology is also extremely versatile, so these high-performance bulk optics I just talked about can work well and be designed for any wavelength, where again, matter-based systems are very limited in the wavelength that they can work with. So our technology is compatible with any quantum system that utilizes single photons as their qubit. So, okay, this all sounds great. You might be wondering how we actually do this, because light travels really fast. Great question. So one approach is just to slap some mirrors on the moon, slap some mirrors on the Earth. Light goes back and forth a few times, and there you go, you have your memory. Unfortunately, this is not very practical. The mirrors would be very expensive, and the moon moves around. So, okay, we bring it back down to Earth. What we actually do is we have free space storage loops. This is a CAD design of a device we've built. So you can sort of see the size scale we're going for. This is a rack-mountable device. And inside, there's a bunch of stuff going on, but really all you need to know is light is bouncing back and forth between these mirrors, and that's how we store it. Basically, what we're doing is we are putting the photon on a treadmill. We're storing it without letting it go anywhere. But there's still a lot going on in this, so to make this a bit more digestible, here's a simplified schematic of what's going on. We have a series of 3 free space storage loops connected together, and in each of these storage loops, we have an optical switch that lets us switch the photon into a storage loop, and it just goes around this loop, bounces off these mirrors as many times as we want, and we switch it back out, and it goes on to the next storage loop. And in these, we have reflection cavities, and in these cavities, the light just bounces back and forth hundreds and hundreds of times, giving us a long free space path length and a really compact space. And this is really what enables us to make a practical, scalable free space quantum memory. So this is what we make. Our products can enable performance enhancements immediately compared to competing systems. We have 2 main offerings. One of them is a fixed delay quantum memory. This is just the cavity. This is just the reflection cavity. And this offers maximum performance for a single fixed storage time. We also have this reconfigurable memory, which is the storage loop I was talking about. And this gives us the same high performance of the reflection cavities in free space, but with the ability for the user to control their storage time actively. We've gotten a lot of interest from different quantum parties. The ones outlined in green have expressed the most interest in us. And we are actually selling a device to Sandia National Labs as our first commercial customer. And we're set to deliver that to them this coming August. And this is our team. We are a team of PhDs through and through, scientists all the way. We have expertise in various aspects of quantum technologies, and we are a spin-out of my PI's lab, Paul Kwiat, from the University of Illinois. But we are looking to grow, so if you are interested in what we're doing, we are looking for help reaching customers, developing our products, and when I graduate Duality at the end of this coming summer, I'll be looking to raise capital in about October. So if you're interested, please reach out to me, and thank you so much for your time. And sorry for the formatting issues. I sent a PDF, but it still didn't work out too well.
Questions? You got 5 seconds to start.
So how do you handle multi-computing there where you need more than one photon? You just stack these up then one at a time, or can you store them in the photons in sequence in this? And
yeah, great question. So it is a multi-mode memory. We can store both multiple spatial modes, so multiple photons simultaneously. We can store different frequency components, so all in the same temporal and spatial mode. And we can also store different photons in a train. We just select the one with that optical switch. We just select the one we want, send it in, and we send it back out. And there is some threshold with, like, we don't want the photons to be so close that they overlap, but it's a multi-mode memory. We can store multiple.
What's the wavelength of the photons and what's the loss of the mirrors? I mean, you get these cavities with a lot of reflection going on.
Yeah, so wavelength, whatever you want. Again, these optics can be designed from UV all the way to infrared. Truly whatever you want them to be. And the reflectivity is 99.999% at any of those wavelengths, sometimes a little bit better than that at a select few wavelengths. But these are state-of-the-art mirrors. This is what basically LIGO uses for their type of system.
So what's the maximum amount of time you can imagine storing a photon with this system?
Fantastic question, difficult question. I've been asked that several times. I see this memory being the winner from 0 to 150-ish microseconds. That's what I'm looking to do. There's also a few one-off systems where between 0 and 50 microseconds, say beating fiber, like being the absolute best quantum memory in the world for 0 to 50 microseconds is what I'm targeting for that. Thank you.
Next up, I'd like to invite Jordan from QTI.
I'm not sprinting up either. Great. What does it mean to be connected? Digital networks have changed the world from enabling us to connect with our loved ones when we can't be together in person to creating a paradigm shift in computation. Recent history tells an interesting story about the evolution of computation, mainly centered right here in the Valley. Not long ago, the personal computer was a standalone device that could perform some useful calculations. But then came along networks and the internet, which has enabled us to access servers and high-performance computing resources, and to share data and computational tasks between distant computers, and fundamentally has changed the way we live. Fast forward to today and the creation of the quantum computer. Much like the evolution of the classical computer, the standalone quantum computer will be able to perform some amazing calculations and solve important and currently infeasible problems, such as accurately modeling nature and biological systems, solving routing and other optimization problems, developing new pharmaceuticals and better batteries, and the list goes on. McKinsey estimates that quantum computing will provide up to $2 trillion annually in value by 2035. But I truly believe that the full potential of quantum computers will not be realized until we can connect them across networks, and eventually, a quantum internet. At QTI, we're working on exactly that. We've innovated to create QEdge, our patent-pending quantum entanglement distribution technology that enables the full potential of quantum computers and sensors by providing connectivity and networking capabilities. We've been developing the core building blocks that will enable us to create the first commercially viable quantum repeater that will enable distributed quantum computing and sensing towards a quantum connected world. It's estimated that the global market for quantum technologies will reach $173 billion by 2040. And with our unique value proposition and as one of the first movers in the space, we believe that we can capture $4.5 billion of that market. But along with the opportunities that quantum computing offers, it also has a dark side if it gets into the wrong hands and poses near-term threats to our current way of life. The encrypted data that we currently send across networks, including the internet, can be decrypted by quantum computing-enabled threat actors. And in fact, those attackers are actively preparing to exploit such vulnerabilities. We've received cautions from organizations like NIST, and we've been informed on timeline by quantum computing roadmaps published by companies like IBM. So at QTI, we're solving this near-term problem using our QEdge technology by integrating it into our first product that we call QSARA. QSARA intelligently combines our QEdge quantum tech with NIST standardized post-quantum encryption algorithms to provide unprecedented data security, cost-effective scalability in building up networks, machine learning optimization, crypto-agile defense in depth, and seamless integration into existing network stacks. We've received early validation from industry leaders like AWS, NVIDIA, and Accenture, and others, even to include our first few commercial purchase commitments. We've got a world-class team in quantum technology, including 2 repeat founders and a previous VP of product security for BlackBerry. So I invite you to join with us in changing the world by building the quantum infrastructure of tomorrow while protecting the networks of today. We're currently in the process of raising a seed round of financing that will enable us to commercially launch our first product, to expand our world-class team, and to secure additional patents to protect our IP. So again, come and join with us on this exciting journey. Thank you.
So your delivery mechanism is the hardware, the end-to-end or the endpoint hardware, and then you encrypt and send through the network. Is that what I'm understanding from your architecture?
Correct, yeah. We've innovated to create a new type of hardware infrastructure that is a hub and spoke model that is much more cost effective to scale up than traditional quantum hardware for data encryption.
And data center ready then, is that like on the core, or is it just still point to point, or?
It's data center ready, not today. We have a prototype today, but yes, that is the architecture. Yeah, in fact, AWS just invested some money into figuring out how to integrate our tech into their cloud environment. So.
No? Good.
Thank you.
Next up, Donghan Lee from Bright Quantum.
So, hello, everybody. So, I am Donghan Lee, CEO of Bright Quantum. So, our company provides affordable single photon sources for quantum computers. So, I don't need to explain this one, so maybe I can skip. But quantum computer is very important, and also the economic effect, the impact will be very, very large. So, there are many candidates, but the most realistic approach will be photonic quantum computing. The reason is they perform quantum computation at room temperature. That's very important, and also fast. So single photon source is a key component for the photonic quantum computers. And right now, they are operating at cryogenic temperature. So that's the problem. So the size is big, and also the price is high. So to solve this problem, we develop single photon sources operating at ambient temperatures. So by a simple process, we can have nanogap structures. So here is about 10 nanometer. So by placing a nano emitter in this 10 nanometer nanogap, we can create very bright and fast and high-performing single photon source. So right now, the single photon system is very large because it's operating at low temperature. So quantum computer should be large. So, but in our case, our system, single photon system, can be very small, size of maybe book. And so it can be delivered at 1/100th the size and 1/6 the price. So this compact single photon system can open new area of personal quantum computer in future. So our system, our single photon source will outperform the conventional one. The single photon efficiency will be much larger, which is very important. And also, the operation will be 50 times faster. The size will be smaller and price will be lower because we don't need a compressor for cooling. So initial target customer will be the manufacturer of mid-size quantum computers using on-demand single photon source. But the ultimate customer will be those working on universal computer, which needs a lot of photon qubits. So we'll have $20 million sales at 2029. So this is very complicated, but because of time. And also, this is for the quantum computing, but also quantum communication field has also very large market. So we'll have a significant portion of our sales in quantum communication field. The quantum computer, the hardware market size will be $57 billion in 2030, and photonic computing maybe $17 billion, and our market will be, we plan to have about $20 million in 2029. So for the team, after getting PhD in the United States, I spent 3.5 years doing R&D at AT&T Bell Labs, and I have 30 years of experience in quantum dot research and 15 years in single photon research. And we have 3 experts. One is expert in single photon measurement, and the other one, another one is a packaging device packaging specialist, and a single photon source fabrication expert. All has a minimum 6 years experience. So our company was founded about 1 year ago, and we are now currently at 90% of completion for the device development. And with this opportunity, we like to secure necessary equipment and develop product real time. Okay, so right now we need like $0.8 million for the equipment and $0.3 million in the working capital. So $0.5 billion will be secured by government funding and $0.6 billion in investment. Thank you.
Is your fabrication equipment standard equipment that's available off the shelf, or do you need specialized equipment to make your product?
They are very common one for the semiconductor fabrication, like E-beam evaporator and the ITA, something like that. So right now we are using the university one.
I very much like the slide comparing performance with Candela's device. My question is, you said you were talking as that was the target in the future. Where are you in terms of what specifications have been achieved so far?
So could you very sorry.
The specifications that you have, I think that was in the future, your target. What have you achieved so far with the prototype?
So right now, we demonstrated a single photon, and then for the performance, like indistinguishability or that kind of performance which is needed for quantum computing. So we need some equipment. So that's why we need money. But except this one, so we are also working on low temperature single photon source like Condelas. In that case, the performance is quite good.
Is photonic-based quantum computing the only quantum system that this is your sort of target market, or are there needs for these devices or sources in other quantum systems?
So for the low temperature single photon source, the target is very limited because it's very expensive. So quantum computing will be the target. But in our case, it's a room temperature one or high temperature one. So it can be purchased by any person working on like a quantum technology using quantum optics. So that's I think that's the initial market. And also for the quantum communication, they don't want to have a big cryogenic system, but our system may fit to their need. So there's more market.
All right, thank you. Yeah, so just like to thank all the presenters one more time. I mean, if you, I promise that, yeah. Like you see, there was a great diversity in the teams. I want to thank again the judges. I want to thank Chloe, Celia, Greg, and Adam. The final winners will be announced at the finale on December 12th. That's Thursday at 4:50 in the main ballroom in the main event. I've also been asked to remind you that there is a major announcement happening at 5 p.m. in a few minutes in the main ballroom. So if you want to head over there right after this. Otherwise, thank you very much for coming. I hope this was interesting. All of the presenters have their names and company names in the agenda. So if you do want to reach out to them, please do. Thank you, and I'll see you on Thursday.